So you've actually got enough to describe everything that happens. I said, and this is probably the hardest part, that we had a symmetric group on some set X. So let's make another definition. A transposition on X is just a function that swaps two of the elements of X. So you can imagine the one that I actually described on my set of two elements, the one that did this, that's a transposition. Now imagine that there were a bunch of other elements out there, but I just picked two of them and said these are the two that I care about for now. Then I can define a function that says anything that's not the two elements that I have my fingers on stays fixed. And the two that I have my fingers on, I'll just swap their positions. Those are my transpositions. So here's an example of a transposition on a set with three elements. A set with three elements is going to be the set 1, 2, 3. It's going to fix 1, and it swaps the roles of 2 and 3. So it's not a difficult theorem, but it's an incredibly useful one. Notice that the symmetric group on X is generated by transpositions. In other words, if you give me an arbitrary function that's one-to-one and onto, I can realize it as systematically swapping pairs of elements and sort of moving my way along. I'll give you a hint about how to do this. You can imagine, just figure out where 1 is supposed to go, and you start with the function that swaps 1 and wherever 1 is supposed to go. And now you sort of keep marching your way along. Does wherever 1 is supposed to go, is it in the right position? Was it supposed to go back to 1, or do I now have to move it? You sort of just keep writing your transpositions as a way of saying, literally, just move your elements into the right position, one at a time, and at the end of the day, you've moved all of the functions, all of the elements into the right positions. That's a sketch of how this works. Okay. So we have, and we've already described, 3 distinct sets on this. We have the edge, and I'm going to call them the edge faces, so it's not just little blocks, but now little blocks together with the color on them. And there's the 12 edges, each of which has 2 colored faces, actually the 24 edge faces. Then I have the 8 corner blocks, and there are 3 faces, so that gives me 24 corner faces, and then I had the 6 middle blocks, which nothing happens with them anyway, so we can go on. So I have a total of 54 faces, only 48 of which matter. So I get 3 symmetric groups associated with this. A symmetric group that's moved the edges around, the edge faces around any way you want. One that's moved the corner faces around any way you want. And one that's moved the middle faces around any way you want. And we already saw that the middle faces are actually fixed, so this last one really doesn't show up. And we see that not every element of these can occur, because actually what we saw was I'm not allowed to just flip edges willy-nilly. If I flip one, I have to flip another one. So I can't just swap them. And I can't just interchange 2 edges. If I do that, then I interchange 2 other edges. So the way that that's expressed and the way they'll show up is anytime I have a transposition that would flip something, I have to have another one that shows up, so a companion that comes along. But I can kind of choose that companion that comes along sort of freely. There's no real restriction on it. It's just that they never show up on their own, they always show up in pairs. Okay, so now let's work out what the group is. Well, I'll just tell you what the group is. And first I'll tell you its size. And this answers one of the questions that I posed at the very beginning, namely, how many possible starting states are there? Because we described, how do I get to a starting state? I take my solved cube, and then I do a bunch of moves to it, and then I look at where I ended up. So every distinct element in the group gives me a distinct cube, and I just have to figure out all the possible ones that show up. And here's how many there are. So this is a lot. If memory serves, this is thousands, millions, billions, trillions, quadrillions. So somewhere around like 43.2 quintillion. It's a lot. A lot. So you should start working now to see if you can enumerate all of them. But it'll be, there's a more compact form for this. And the way I'm going to write this, I need another group, and we actually have all the terms we need for this. So I'm going to let the alternating group on X be those elements of the symmetric group. such that I say f is even. What that means is I can write f's an element of symmetric group, so I can write it as a product of transpositions. I count how many transpositions that took, and I ask, is that even or is that odd? And if it's even, it goes in the alternating group. If it's odd, it doesn't. So something you should be asking is a really good question, and that is this even well defined? Because I could say, I could take two different lists of transpositions that describe the exact same thing. It's actually really not hard to write down sort of redundant lists, really long transpositions that do really simple things. And sort of, you can try and be as pathological as possible. Turns out the number of transpositions needed is not well defined. Whether that number is even or odd is well defined. So anytime I tried to do a different one, I'd have to introduce two transpositions to change it around. Okay, so then this is the group. And I should say, all of these are old friends. This is the modular arithmetic group, z mod 3 that we saw. This z mod 3 to the 7th, I'll come back to why it's to the 7th, but you should think of this is exactly the ways I can orient each of my corners. So remember, I could orient them. I'm actually doing sort of an obvious rotation of order 3 with my hands, and we actually saw the rotation of order 3 being done. So that's what these are. Why is it to the 7th, not to the 8th? Well, remember, when I did my orientation, when I did a change on my orientation, change one of them any way I wanted, but it would also change another one in the inverse way. So remember I said that the sum of them always had to be fixed. So I can fix that sum to always be 0. And that cuts down a degree of freedom. So it's not that I had one for all the possible corners. What this is telling me, if you know the orientation on 7 of the corners, then you know the orientation on the 8th corner, because it's the only thing that works to make the sum of all of them 0. Similarly, this one, this is the possible orientations of each of the edge pieces. There should be 12 of them, but again, whenever I flipped an edge, I also flipped another edge. So the sum of those has to also be 0. So you can think of this as the collection. I can arbitrarily choose the orientation on 11 of my edges, but then the orientation on the 12th edge is fixed for me. This is the alternating group on the corners. This is the alternating group on the edges. And so remember, I looked at the corners, and I saw I could take any two corners and swap them, but I had to also swap two other corners. So in other words, I had a pair of transpositions that acted on the corners. And in fact, I did any pair of transpositions acting on the corners just by choosing it better. There's a small set of transpositions you can check or generate. Similarly, I could rotate the edge pieces around, and I showed a picture of the rotation. And if I have all of the rotations in a face of edge pieces around, then I actually get any of the possible rotations in edges, any of the elements of the alternating group there. So this last z mod 2 that I didn't talk about shows up here because there's also a move that I don't have a picture of, but what it does is it swaps two corners and it swaps two edges. So it doesn't say it either. It sort of is a slightly different, but it's the only other option. Okay. So it's a very, well, it's a very, very big group, but not